Hi guys. Okay, so we're going to cover the last part of chapter 6.9, which deals with the attractive forces in the molecules. And these molecules are the covalent compounds. And these are also called the intermolecular forces, or in other words, IMF. So intermolecular forces. So these attractive forces that exist in between the molecules that define the properties of those molecules. So there are three types. One is the dispersion force, dispersion forces. And the second is the dipole-dipole, and for some reason, it's said it twice. And then the third one is hydrogen bonding. Hydrogen bonding. Okay, hydrogen bonding. All right. Now we have the dispersion forces are going to occur in between the particles that are diatomic. So first look at the dispersion forces. Diatomic molecules only, sorry. Okay. Dispersion forces. So what do they look like? Dispersion, like I said, dispersion forces exist between the diatomic molecules. And those diatomic molecules are like hydrogen. Diatomic molecules are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. All right. Okay, so here, what's happening? The way these atoms, they align, you know, the way they are, the way they, you know, they connect with each other. How does this happen? Okay, here it is. Let us look at bromine, for example. Bromine molecule has two bromine atoms singly bonded. Okay, this is a single bond. And that's fine. But remember that bromine, the electronegativity is very high. Okay, the bromine's electronegativity is high. So by this, it looks like it is equally sharing the electrons. But the reality is at some point of time, one of the bromines is going to exert its power. So in other words, it will attract the electron clouds towards itself. So temporary dipole is going to come in this molecule. Although this is a neutral molecule, right? Both the bromines together, even if they are pulling the electron clouds, it should be with the same pull. But in that tug of war, momentarily, one of the bromine pulls it stronger than the other. And when that happens, it gets a delta negative charge. The other one gets the delta positive. And this sign means delta, and delta means really small sign. So it's a very temporary small charge. But anyways, that negative and positive has developed. So what happens now, another bromine, the same story is happening in another bromine atom also. So here is this other bromine, a bromine molecule, and this guy will, so the way they align, the negative of one is aligned to the positive of another. Okay, so this is, sorry, this is the bromine. Let's do another one. So this is another bromine, and this is another bromine, sorry. So this is actually a proper bond, not just the way I'm showing this dotted line. No, it's actually a proper bond. And so we have another bromine here, another bromine, and let me just do one more. And so this is how the negative of one is close to the positive of the other. The delta positive of this one, negative of this one. Delta positive here, delta negative here. Delta negative here, delta positive here. Delta negative here, and delta positive here. But what happens is that when this charge develops, the bond breaks. So this bond breaks whenever the charge develops. And now the bromine forms another bond, and that new bond is with this one. So this is this one, this is this one, this is this one. These two will form bond. These, yeah, and then one of them will form. So anyways, so this one and this one will form bonds like that. And so this is what happens. So anytime a new bond is formed, then again the same story repeats. They're going to break up, and this and this is collecting. So bond breaking and bond making continues to happen. Okay, bond breaking and making happens, continuously. Continuously this is happening. So this is happening with, even with oxygen with the double bonds, and even with the nitrogen with the double bond. Same thing, this thing. So this is the dipole-dipole attraction. Okay, I'm sorry, this is the dispersion forces. So yeah, the temporary, that dipole is formed, but this is a dispersion forces. Okay, next let's look at the dipole-dipole attraction. Dipole-dipole attraction. Okay, so here dipole, for example, you have hydrogen on one end, and you have, these are two different atoms. So this happens with the same atoms. Okay, a molecule made up of, happens in the molecules made of same atoms. Dipole-dipole happens in the molecules that are made up of different atoms. So molecules made of two or more, also, it doesn't matter, two or more different atoms. Okay, so here what is happening? In this case, hydrogen and chlorine. Hydrogen is less electronegative. So the electronegativity of hydrogen is less than the electronegativity of chlorine. And we've discussed this quite a bit in the previous lectures. So by this time, you should just know that chlorine is more electronegative than hydrogen. Chlorine gets a delta negative charge, hydrogen gets a delta positive charge. The heat map of this molecule looks like this. So here is this hydrogen, and this is this chlorine, and you have, sorry, this guy is, chlorine is right here, hot region, and hydrogen is cooler comparatively. It's cold, it's small and cold also. So we see that the electrons are spending more time towards chlorine because of this delta negative charge. Chlorine delta negative, hydrogen delta positive. Okay, so yes, this becomes a polar molecule, and we discussed polarity already in the previous lectures. Okay, so this is a polar molecule. Now, how does it align? So every hydrogen is close to the chlorine. So here's this hydrogen, and this is chlorine. The way, so here the bond is not going to break. So every chlorine, it's just that the way are like the way they sit with each other. This is how they sit in a, sorry, hydrogen here and chlorine here, hydrogen here and chlorine here. So you see this is the attractive forces. Hydrogen has a delta positive, chlorine delta negative. So there's always an attraction between positive and negative. There is attraction in the molecules. So this part is positive is close to negative. Positive is close to negative. And here is this positive, negative, positive, negative, negative, positive, negative. Okay, so we see that these guys are, this negative side are aligned. It's just an alignment, and the positive sides are aligned in this way. Certainly the positive, there's going to be repulsion, but positive, negative, they stabilize like this. Okay, so this is the way they arrange. So that's the dipole-dipole. Now, another dipole-dipole I want to show you is this type of molecule. For example, you have carbon, double bond, this, and this is the CH3, and CH3. Okay, so keep this in mind that this site is a like a non-polar site, whereas this site is the polar site. Why? Because oxygen has the highest, the electronegativity of oxygen is the highest. So let's just put this here. Electronegativity of oxygen is higher than carbon, and carbon is higher than hydrogen. So you're going to refer to the handout, and you can check for the numbers on the handout. You can check for the numbers of the electronegativity values, but at the same time, you can also look at the trends in the periodic table. And so that's trends in periodic table will also tell you the same thing. Okay, anyways, now let's focus on this. So we see that these two guys are non-polar. Now, remember all the time, always remember, let me put this in red. Remember, carbon, hydrogen bonds are non-polar. I mean, although carbon is more polar than hydrogen, so technically, mathematically, it should be a polar bond, but right, it's at that 0.4. The difference in the electronegativity is 0.4. So by default, we just consider it to be a non-polar bond. Non-polar bonds are also hydrophobic. Now, what does this mean, hydrophobic? Hydrophobic means hate water or are afraid of water, okay? Now, on the other hand, this piece is, so this is here, these two, okay, these carbon hydrogen. So this carbon oxygen bond is polar. This is polar bond. And when it means polar, because oxygen is more electronegative comparatively, so the bond is also very polar. So that's why the difference in the electronegativity is higher. Okay, so as a result, oxygen a delta negative charge and carbon is delta positive charge. So we leave the non-polars because there's no charge. Anytime you have something non-polar means no delta positive or delta negative charges. So this part of the molecule is like a grease, like oil. Okay, like oil hates water, so those things. Okay, so anyways, now how do they align? So look at this. Here is this oxygen, double bond carbon, and the CH3 groups can also be just written like this, like a line, So in that line, this piece is the CH3 group. This part right here is the CH3, and R is the rest of the molecule. R is rest of the molecule, and it could be, anything. But as far as this piece is concerned, this is CH3, this end, this corner. So I'm going to just put it like this. So this is all organic chemistry, okay? Now, remember that the way this is going to align, oxygen is delta negative, carbon is delta positive. So the oxygen is going to come and be attracted to carbon, and the CH3s are hanging off on the sides. So every positive end is aligned with the negative end. Okay, so of the neighbors. So this is one neighboring molecule. This is one neighboring molecule. Sorry, this is one neighboring molecule. Okay, this is one neighboring molecule. and the other one is this one. And then comes the next one. And then comes the next one. So this is how they sit on each other. So we will just go and just finish this off. Oxygen, double bond, carbon, and CH3, CH3. Oxygen, double bond, carbon, and CH3, CH3. Every oxygen is attracted to carbon. And sorry. Okay. Every oxygen is connected to carbon and every carbon is connected to oxygen. So this is how they are aligned like this. Okay, so that's these are the properties. Similarly, if you have, so this is the dipole. This piece is the dipole in this molecule. This is a dipole. This end is a dipole end. This is a dipole. So every time you have positive and negative in one side, that's dipole in a molecule. Okay, dipole. All right, now let's look at another example. So these are just different examples of dipole. This is one, this is the second one, and let's look at the third one. 1, 2, 3. Okay, now here we have, for example, CH3, CH2, 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 CH, and 1, 2, 3, 1, 2, 3, 4, 5, and let's just put it here, OH. So you see, we talked about that carbon and oxygen are polar, and oxygen and hydrogen is also polar. So this side of the molecule is polar, very polar. This whole piece is a very polar piece. However, this side of the molecule, where there is lots of carbon hydrogen bonds, we already talked about, that's like a greasy end, hydrophobic end. So this end is the non-polar side. So this is the non-polar side, non-polar end or non-polar side, and this is the polar side. And when this is the polar side, that means there is a polarity in the molecule. Okay, so remember that OH bonds are always going to be polar bond. Anytime you see OH in a molecule, no matter how many OHs there are, always going to be polar. Anytime you have carbon and hydrogen bonds, always that's going to be non-polar. Always. So anything that I write in red is like really, really important. Anyway, so here we have these polar and a non-polar sides. So overall, this molecule becomes a polar molecule because it has dipole. So this is a polar molecule and it has because of dipole. So dipole is not just, having the two side, the charges. Obviously, if you look at it, yeah, this hydrogen has delta positive and this oxygen is delta negative. So just by that, there is a dipole in this molecule. Okay. All right. So that's one piece. Now, there is also something that your book has not stated very clearly, and that is I'm going to just put it as here, is a temporary dipole in dispersion. There is also dispersion forces. So we will just and these are the London dispersion forces, which are more common in all the molecules. So London dispersion forces, London dispersion forces. Okay, let's look at those also. So 1, 2, and now we are looking at the London dispersion. Actually, one second, I should have, okay, it doesn't matter. Okay, here is the London dispersion. So London dispersion is in all the molecules. Dispersion, just dispersion is in dispersion, just dispersion is in diatomic molecules. But if you look at just the London dispersion forces, these are also called LDF. LDF. These are present in all molecules. So if we are talking about London dispersion, now this is not very clear, as I said, written in your book. So just make sure that you know, if you pick up another book, you will see London dispersion is present in all molecules, okay? So let's look at this. How does this mean? London dispersion is just spread of electron cloud. Spread of electron clouds, how the electron clouds spread. So in the end, you know, look at these examples and how they affect the properties of the molecule. Let us say you have this guy, C, 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 and C. So H, 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 and H. So H and H, and then like a ball, right? So the spread of the electron cloud of the C5, and then look at the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, C5H12. So can this molecule can have the arrangement of carbon and hydrogen bonds like this, or it can be like this, CH3, and then CH2, and then CH2, and then CH2. So 1, 2, 3, 4, and 5, H3. So this is still 1, 2, 3, 4, 5 carbons and 12 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so both of them have C5, both of them have 5 carbons and 12 hydrogens, both of them. Okay, but there is a difference how the electron clouds manifest. So look at this. This electron cloud is like this in reality. Yes, this is a branched, structure, branches, but the electrons that are being shared, eventually they all spread out. And so the spread is like that. It looks like a ball. This one looks like a mattress. So the arrangement is still, but it's a linear arrangement. And in this linear arrangement, it's like a mattress kind of feel. So here, when the molecules are going to connect, in the first one, they like when the molecules are close to each other, so they are like balls and they just barely touch on the side. So I'm going to just put it here. So they're just touching the little piece, this little thing. So they stack against each other like balls, right? If you've seen in the gyms or in these play structures for the children, you will see the balls, they get stacked up one on top of the other. Matrices, this guy is like a mattress. So 1, 2, 3, 4, and 5. So another molecule comes, which also has this shape, like a mattress, 1, 2, 3, 4. So this is how they are stacked. Okay, so when they're stacked like this, now keep this in mind that they will both have the same molecular weight. Okay, but their boiling points are different. Boiling point is different. And their state in which they exist is different. So this exists as a gas and this one exists as a liquid. Because, see, here it is, boiling point means the heat that you add to convert a liquid to a gas state, right? That happens when things boil. They convert from a liquid to a vapor state or a gas state. So the first one, the molecule A is going to need less energy. Less energy means low boiling point. Low boiling point. And the second one is going to have a higher boiling point. The way the molecules are like connected to each other, is it easy to dismantle or not? So when we talk about the boiling point, yes, we are talking about dismantling the attractive forces in the molecules. Attractive forces in the molecules. So in the first case, look at the attractive forces. The attractive forces are just a little bit connection right here. Let's put it in a darker color. So here, or blue. Okay, so just connected at this point, all these balls just touching at a very little, surface, that small area, they're just touching, barely touching. So when you kick the balls, what happens? The balls begin to move on their own. So when you kick the balls, they move on their own. And as they move the other balls also. So they start rolling on their own, and a little bit of energy with less energy, like little bit of kick, they dismantle. Or in other words, this thing, they roll over, they start rolling. Okay, so this is what it means. So in a liquid state, they are arranged in that ball structure, but you provide heat, little bit of heat, and they begin to, dismantle and become like gas. And gas particles are spread out more. Liquid particles are close. Gas is spread out more. So that's why the boiling point is less, low boiling point. Low boiling point, and they actually exist as gas at room temperature, and room temperature is 26 degrees Celsius. On the other hand, look at the surface area of these guys. They're like touching every single part, like mattresses are placed one on top of each other. So every single part is touching. So you not need to give a lot of heat to convert this liquid state to a gaseous state, to dismantle them. Okay, so with less energy, they start rolling. Okay, and here you need to give lots of energy so that it, so mattresses can be removed. So did I write this down? This is like a ball arrangement. This is like a mattress arrangement. Okay, so give lots of energy. So give lots of energy so the mattresses can be removed. Okay, or dismantled. So that lots of energy is high boiling point and low boiling point. And as a result, these exist as liquid at room temperature. At room temperature, that is at 26 degrees Celsius, because the molecules are strong attraction. So that's why its arrangement is that of mattress. So here we will see weak attractions in the molecules. And here you see strong attraction in the molecule. All right. So we have these two examples, A and B, and how the molecules are arranged and stacked. Now comes the last part, which is so keep this in mind that all molecules have London dispersion forces, because it's just a spread of the electron cloud which determines the properties of these molecules. Okay, next is you are going to study is the hydrogen bonding. Now keep this in mind that hydrogen bonding is not bonding between the hydrogen atoms, but anytime you have hydrogen attached to oxygen, hydrogen attached to nitrogen, and hydrogen attached to fluorine. So it's always just the oxygen, nitrogen, and fluorine. When hydrogen is attached to them, only then, you know, oxygen, only then the hydrogen bonding occurs. Okay, hydrogen bonding it's due to hydrogen bonding water freezes at 0 degrees Celsius and boils. Boiling point is very high, boils at 100 degrees Celsius. Very high. Okay, so what is that? So here's the thing. Here's this oxygen. Here's this hydrogen. This is a water molecule. Okay, oxygen, hydrogen. So remember that water molecules are bent molecules. Water is very polar, but just bent. Okay, so this. Okay, so here water, remember that oxygen has these lone pairs, and hydrogen and oxygen bond is very polar. So as a result, there is going to be, oxygen is more electronegative than hydrogen. So oxygen has a delta negative charge. Each of the hydrogens, because it's a polar bond, will have a delta positive charge. Sorry, delta positive charge, delta positive charge, delta positive, oxygen delta negative, hydrogen delta positive, oxygen delta negative, delta positive, delta positive, delta negative, delta positive, delta positive. Okay, delta means small. So this is the water molecule, bent molecule, first of all, and then there is a polarity in the molecule. So what happens? Remember, intermolecular forces are in between the neighboring molecules. It's always the neighboring molecules. It's not inside the molecules. Inside the molecules defines the molecule in general, like the shape and the polarity, but intermolecular forces is in between the two. So what is happening? This oxygen connects with this hydrogen because temporarily gives its lone pair to the hydrogen. Because remember that that oxygen is drawing the electron clouds towards itself. So here is this water molecule, hydrogen, one side, and here we see is the two dots. Hydrogen is delta positive, this hydrogen is delta positive, and here comes this. All right. So this is the polarity. This is a very polar molecule. So remember that this oxygen and this oxygen is pulling the electron clouds towards itself. And there is a lone pair on carbon, oxygen, so that makes it very polar. And then hydrogen is so kind of unfairly treated because oxygen is highly electronegative. So because of all that, the neighboring oxygen lends its lone pairs to the neighboring hydrogen. So this oxygen lends its lone pairs to this hydrogen, and a very weak electrostatic attraction exists between the neighboring oxygens and the hydrogens, like that. And this is a network now. So this is a network. Okay, this one already got. So that network that exists, so this is here, This is this network. So this is, I'm going to just put it in, this is hydrogen bond. So it's between the neighbors, hydrogen bond. So it's a very, very weak electrostatic attraction exists between the molecules. Between the molecules, but between the oxygen of one water molecule and hydrogen of another water molecule. Okay, so that weak and electrostatic attraction, which is responsible for the higher boiling and the higher melting points of freezing points. Boiling point is very high because of that. And if you compare, oxygen is present in group 6A, sulfur, water at room temperature. So that's the thing, you know, H2S versus H2O. H2S is a gas at room temperature, but water is a liquid. So remember, liquid, the particles are very close, and solids, they are extremely close. And gases, there's no attraction in the particles. So it's liquid at room temperature, and room temperature, as we said, RT, room temperature is RT, and that is 25 or 26 degrees Celsius generally. Okay, so because the water molecules, it is because of hydrogen bonding. This is the reason why. Okay, in the water. Now let's look at an example where ammonia. So here's this ammonia, nitrogen, and nitrogen. Same thing with nitrogen also. There's a lone pair on the hydrogens, and there are 3 hydrogens, a lone pair on nitrogen, 3 hydrogens, and we have these hydrogens delta positive, nitrogen delta negative. Okay, so the polarity, because nitrogen is more electronegative, nitrogen is more electronegative than hydrogen. So therefore, the polarity, and moreover the lone pairs, anytime there is lone pair on a molecule on the central atom, it's always going to be polar. So anyway, so here's the hydrogen bonding in nitrogen. So nitrogen, this has this 2 lone pairs and 1 lone pair, sorry, hydrogens. And so this so just to show you in these molecules, and we have here, so hydrogens are delta positive and nitrogens delta negative, delta positive, delta positive, delta positive, delta negative, delta positive, delta positive, delta positive. And so what happens here, we have this is the hydrogen bonding that exists between this nitrogen and the neighboring hydrogen, this nitrogen and the neighboring hydrogen. Okay, and so that causes, this is the hydrogen bonding. Okay, that occurs in this molecule. Okay, so you guys have to just see that, look at this molecule, CH3OH. So just by the presence of this alone, there's going to be, and this is, so this molecule has, yes, it has got this side, which is non-polar side. This is non-polar. One side is polar. So this molecule will have London dispersion forces are present in all the molecules. Number one. Number two, there is dipole-dipole because one side is polar side and this is the non-polar side we talked about already. So there is the dipole present, okay? And this, the third is because of this OH bond. Because of this OH, oxygen delta negative, hydrogen delta positive, and oxygen will always have these lone pairs. So this is responsible for hydrogen bonding. So this molecule will have hydrogen bonding also. Hydrogen bonding also. Okay, so anytime it's the OH bond, that is hydrogen bonding. All right, guys, so this completes this chapter. If you have any more questions, please don't hesitate to contact me and I'll be happy to assist you. But right now, that finishes this chapter. All right, thank you. Take care. Bye-bye.